Hi, welcome everyone. I'm Rich Stone, HHMI. I'm be moderating this talk today. I know practically nothing about AI, so I'm going to need your help during the Q&A. Be ready with questions. So it's my pleasure to introduce our speaker today, Sayash Kapoor. So Sayash Kapoor, Princeton University, his research at the Princeton Center for Information Technology Policy focuses on the societal impact of artificial intelligence. He previously worked on AI in both industry and academia at Facebook, Columbia University, and EFPL in Switzerland. He received the Best Paper Award from the Association for Computing Machinery and the Lasting Impact Award from the ACM Conference on Computer-Supported Cooperative Work in Social Computing. He is co-authoring a book about AI snake oil, critically examining what AI can and cannot do. He and his co-author were recently named to Time Magazine's list of the 100 most influential people in AI. So Sayash is going to talk for a while, then we're going to do Q&A with him right after that. And just before he starts, for those of you interested in AI, I highly recommend Ross Anderson's piece in The Atlantic this month. It's about Sam Altman and ChatGPT. And the title of the article is, Does Sam Altman Know What He's Creating? It's a fascinating take on the potential and the risks of AI, really eye-opening, will make you think. So if you've read that and have questions about that, Sayash may be prepared to answer those as well. So without further ado, Sayash, it's all you.
Thank you so much for that introduction, Rich, and thank you in particular to Amber Dance for inviting me to be here in front of you all, and also to Rosalind Reed, Sylvia Cantor, and Randall Culpepper for making sure I had the ability to be in conversation with you all, even virtually. So it's my pleasure to be here. It's a pleasure to talk to you all about AI and its hazards for science. Before we begin, just a very quick overview of what's in the presentation today. So we'll begin with a very high-level overview of what AI is, and in particular, what its most dominant paradigm, machine learning, is, and what the difference between the two is. We'll then move on to three substantive sections. We'll look at the role of companies, researchers, and journalists in propagating information about AI, but also in spreading the hype around AI. All right, so without further ado, let's dive in into the first part of the talk about what is AI. So despite all the conversation about AI in the last few months and years, and despite all that has been said and left unsaid about it in some ways, it's really hard to give an overarching definition of AI. I think there is no real consensus on what constitutes AI. But for the purposes of this talk, as well as for the purposes of talking about AI more generally, I found that three loose criteria can help understand whether something falls inside this definition or outside of it. So the first part of the definition is the tool doing something that usually requires either creative effort or training for humans? So for instance, a lot of the recent advances in AI have been in things like image recognition. You might use AI, let's say on your Google Photos app, in order to classify images of people automatically. And this is something which might not require a lot of effort for humans, but still does require some creative effort on the part of humans. And so what this means is that it sort of falls under the first definition of AI. The second sort of behavior is whether the characteristics are directly specified in the code by developers, that is, whether they're hard-coded into the software, or whether this behavior is not directly specified at all. And for instance, if the system learns from examples. So once again, going back to our previous example of image classification, let's say you have images of cats and dogs on the one hand. One way to classify these images would be to come up with a set of rules. So for instance, if something has whiskers, it might be a cat, and so on. Another way to classify these images automatically would be to give lots of examples of what constitutes cats, so basically images of cats, and lots of images of dogs, and have a machine come up with these rules for specifying which images constitute a cat and which ones constitute a dog automatically. And again, for this part, when the behavior is not directly specified in the code, that's when we refer to something as AI more often than not. Finally, the third criteria is there should be some flexibility in the inputs. So going back again to the last example, if the system only works well on inputs that it has already been trained on. So for example, if a model works well on images of cats that it has already seen and knows the correct answer for, but it does not work well on a new image of a cat or a new image of the same cat even, then we would not really consider it AI. So there should be some flexibility in the inputs on which the model works well. So once again, these are like three overarching, loosely defined ways to tell if something is or is not AI. As I mentioned before, there is not like a specific thing. In most cases, AI has a you know it when you see it type of characteristic, but I think these three criteria somewhat capture what we mean when we call something AI. All right, so having had like a somewhat high-level understanding of what AI is, what is machine learning? So machine learning is the current dominant paradigm of AI. It refers to learning patterns from data, and most prominently, like it is used most often when you learn from existing examples. So when you learn from, for instance, the many images of cats and dogs, if a system learns to recognize what a cat is and what a dog is, that's an example of machine learning. Now, it might not be always like as straightforward as it seems. So for instance, here's an image of several labradoodles as well as fried chicken. And at first glance, many of these images look very similar to each other. But it turns out that the modern machine learning methods that we have are actually pretty good. Given lots of images of dogs, that is labradoodles, and lots of images of fried chicken, we have methods that are actually pretty good at distinguishing between the two, as long as we have labels for each of these images. Similarly, to create tools like ChatGPT as well, we use a different type of machine learning. It's often known as self-supervised learning, but the label is not so important. What is interesting here, though, is that the labels are created automatically from large amounts of training data. So instead of a human having to label each specific image of like a labradoodle or fried chicken, we can actually generate these labels automatically in this case. For example, if you have a sentence, what is your name? ChatGPT is trained to predict what missing words in the sentence are. So one example in its training corpus would be, what is your blank? And the correct answer would be name. Similarly, it would be, what is blank name? And the correct answer is your, and so on. So given enough such examples, essentially all that language models like ChatGPT are learning to do is fill in the blanks. The only difference between ChatGPT and previous methods is that the language models that we have today are trained on vast amounts of data. So a lot of data from the internet, a lot of labeled data generated by humans, and so on. But I think at the end of the day, it's important to remember that machine learning tools are learning patterns from data. In many cases, the labels for these patterns are human generated. For instance, for image classification tasks like distinguishing between labradoodles and fried chicken. But for modern tools like ChatGPT, a lot of this data is generated automatically. So we don't need a human to label this data. We can just convert existing data, say on the internet, into labeled data by converting it into like a fill in the blanks task. All right, so that was like a technical overview of what constitutes the dominant paradigms of AI today, which is machine learning. But I think more important is the distinction between what different types of AI are actually used for in the real world. And that's where we can understand where a lot of the confusion around modern AI methods comes from. So as this image sort of shows, AI is an umbrella term. The same term is used to refer to very different kinds of applications. Some of them work really well. So for instance, generative AI tools like ChatGPT, which is used for generating text, or DALL-E and Midjourney, which are used for generating images, work pretty well at doing the intended job, which is basically generating text or images that can be convincing. And the ethical issues with these tools arise precisely because they might seem to work too well. And so there might be misinformation or over-reliance on these tools. For instance, I think a couple of months ago, a lawyer used ChatGPT to generate citations for a legal case. Each of these citations was made up, and the lawyer was in fact reprimanded by a judge for putting in false citations in their case. And this happened precisely because ChatGPT seems to work too well, despite not having any factual basis for a lot of the claims that it makes. Similarly, there are tools on perception. So perception AI is basically AI that's used to automate perception tasks like looking at things or hearing things and so on. So this includes things like speech to text. I'm sure a lot of you have used transcription tools during interviews to transcribe text, Shazam for detecting what song is playing in the background, or even the image tagging tools that we just saw. So things which can automatically label what's in a photograph. And these tools have been widely in use on social media platforms, but also on photo libraries like iCloud Images and Google Photos. Now, once again, while these tools work well, the ethical issues arise precisely when they start to work too well. So for instance, one example of perception AI is AI that's used for face recognition. And there have been lots of issues, lots of ethical issues with the use of face recognition technology. For instance, because it might enable mass surveillance, especially on the account of authoritarian governments. So these two types of AI broadly work well, but there are lots of ethical issues. The third kind of AI, the third major kind of AI application that we see is AI for predicting people's futures. So all over the US today, AI is used for predicting recidivism. That is, whether a defendant currently on trial would go on to commit a crime if they were released. It's also used for detecting fraud. It's used for predicting what some job applicants' job performance would look like if they were to be hired. Now, this type of AI is drastically different from the other two. We have very limited amounts of data. There is a lot of noise inherent in the process of predicting someone's future, mostly because people's life trajectories are not fixed. And so in general, these tools perform much more poorly compared to like the other two. So prediction AI performs much more poorly compared to generative and perception AI. And this is where we feel a lot of the snake oil is. So we'll now move on to the role of companies in AI hype, and we'll start with what we were just talking about, which is that companies exploit the public's confusion over how well different types of AI can work. So for instance, here's an example of Retorio. Retorio is a company that's used precisely for the example of job performance prediction that we talked about. So their pitch is that they can use AI to predict which person would be a good candidate to hire. Now, it turns out that this type of AI is extremely brittle. In fact, on the right-hand side, you can see an amazing takedown or deconstruction of how this type of system works, where someone used the exact same interview. They gave a video interview of themselves, except when they added a bookshelf as their Zoom background, all of their scores went up by a lot. So this just shows you that instead of focusing on the content of these interviews or on focusing on the actual signals that might actually signify if someone is going to be like a good candidate for a job, these AI tools are picking up superficial relationships like what's in someone's background or whether they're wearing glasses or headscarves. And in fact, a lot of these relations, as you might imagine, also tend to be extremely biased. So in one example, if you darken the image, that leads to worse results for a job applicant. Now, job performance is already a pretty consequential example of what might go wrong if we use predictive AI applications. But there are some examples which are even worse. So for example, in the 2013, the Netherlands deployed an algorithm to detect welfare fraud. That is, which of the people who are taking welfare, which ones might be committing fraud. It was used for 6 years until 2019 without being challenged. And over those 6 years, it wrongly accused thousands of families of welfare fraud and sent many into debt. So around 30,000 families were accused of committing fraud with their welfare applications. Many of these families were asked to pay back over 100,000 euros. And when the scandal was unveiled, the entire Dutch cabinet and the prime minister resigned, in part because of this scandal. Even in the US, I think we've seen many examples of predictive AI going wrong. So in 2017, the healthcare technology company Epic launched a sepsis prediction algorithm. So sepsis is a disease that is responsible for the vast majority of deaths in US hospitals. 1 in 5 people worldwide die because of sepsis. It's an infectious disease. And in particular, if sepsis can be predicted early, then people have the highest chance of survival. For instance, because they can be prescribed antibiotics. Now, once the algorithm was deployed with a claimed AUC of 0.76 to 0.83. So you can broadly think of AUC as a measure of accuracy. 0.5 means that the algorithm is basically like random. It is basically doing a coin flip for each patient. And when the algorithm was deployed, Epic claimed that they had an AUC of 0.76 and 0.83, so around 0.8, which is generally considered a good AUC figure. 4 years later, in 2021, an investigation found that the AUC was actually much lower in clinical settings. So it was 0.63, much closer to random than initially thought. After these findings and after a lot of investigative journalism on what exact model Epic was using and how well it performed in the real world, in October 2022, Epic discontinued this model from being sold in hospitals. But as you can imagine, by then already a lot of damage has been done. In particular, the model had been used for 5 years before it was discontinued. Finally, another example of things going haywire with predictive AI is with bias. We've seen one small example earlier. Here's another one. So an Associated Press investigation found that Oregon, the US state of Oregon, had implemented a child safety screening algorithm to predict which children are at risk of maltreatment. Now, you can imagine this is an extremely important problem. In particular, if we can predict which child is at risk of being maltreated, we might be able to intervene earlier in their lives or provide more care and so on. But it turned out that there were widespread reports of bias against Black families in similar algorithms. So even given the same risk of a child being maltreated, Black families were much more likely to be flagged as harmful or potentially abusive. And so after widespread report of bias in such algorithms, the tool was discontinued in 2022. The thing that's common across all of these examples is that these are all examples of predictive AI. So in all of these cases, we try to use AI to solve a social problem by predicting the future. But we have very little evidence to actually say that AI is good at solving these types of problems. So with this, we sort of move on to the next part of the talk, which is about how machine learning-based science constructs its evidence and what we can do to find out about these problems before they actually occur. And in particular, we'll start with an understanding of how do we even tell if an AI system can perform well in the real world. So the dominant paradigm today in machine learning to tell if something is performing well is what's often known as the benchmark datasets paradigm. That is, you train AI systems on one part of the dataset, which is often called the training set. And then you test the AI system on another part, which is completely separate. This is called the test set. Now, this separation between the training and the test sets is extremely important because otherwise AI systems can memorize all of the details in the training set and get exceptionally high accuracy numbers, but this performance will not translate into the real world. So in other words, if you train AI models on the same data that you test them on, you're essentially teaching to the test. Now, the violation of the train test split assumption leads to one of the biggest issues in AI systems. It has impacted systems in a lot of engineering as well as machine learning-based science settings, as we'll see in a minute. And in particular, this was one of the reasons why Epic's sepsis prediction algorithm failed in the real world. So the assumption is that you're always testing the models on a separate data set from what it was trained on. So this error is known as data leakage. What it leads to is a spurious relationship in an ML model. So the machine learning model, as we saw, is only detecting patterns in data. And when we use the same data set for training as well as testing a model, it leads to inflated estimates of model performance, like we saw with Epic's sepsis prediction tool. So here's one quick example to see the impact of leakage and how it actually arises in a real world application. So here's a stereotypical example of a machine learning model, very similar to the Labradoodle versus fried chicken example that we saw before and the example of cats versus dogs. That is, can machine learning models distinguish a wolf from a dog? So in particular, given enough images of wolves like the one on the left and enough images of dogs like the one on the right, machine learning examples can actually indeed do a very good job at detecting between these two species. And this might make sense because image classification is a kind of perception task, and perception tasks are something AI particularly shines at. But what happens if we flip the background? So now the wolf, instead of being in a snowy background, is on a grassy field, and the dog, instead of being in a park, is on a snowy field. In this case, it's not so easy for the model anymore to determine which dog or which image is of a dog and which image is of a wolf. And in particular, this is because all machine learning models are doing is relying on correlations to determine which image is of a dog and which one is of a wolf. And so it turns out that the background color is an extremely important or extremely feasible thing to rely on if all of the images in the training set are from dogs are on grassy fields and all of the images of wolves are in snowy backgrounds. It's actually like a reasonable sort of conclusion to draw that things on grassy backgrounds are dogs and things on snowy backgrounds are wolves. So this is a classic example of leakage because one of the features, that is the color of the background, is what is causing the machine learning model to detect something as a wolf versus a dog. That is, it is not actually great at species detection. What it's actually doing is detecting the background color of the images. So let's look at a few other examples of leakage and how it arises in machine learning models. So one of the easiest or one of the most sort of prominent examples of leakage is when the data set that is used for evaluating an AI tool is not actually separated between a training and a test set. This is a textbook example of leakage, but still surprisingly common. So in particular, here's on the slide, we have a review from the JAMA Psychiatry Journal, led by Russell Polrak at Stanford. They looked at 100 papers from neuropsychiatry and found that 45 of these papers only ever looked at performance numbers from the training data. Now, this is essentially teaching to the test. In fact, all of these performance numbers are likely to be significantly exaggerated. And yet that is the standard at which a lot of the machine learning based science that we see today is. Another example of leakage is when we use illegitimate features for the task at hand. So consider a system that's being used to predict for an incoming patient to a hospital, whether that patient will actually end up getting hypertension. And say that the data that's used for training this model is past health ailments, the age of the patient, and whether the doctor has ordered hypertension medicine. Now, one of these features, as you might be able to guess, is not like the others. Because if a doctor has already ordered hypertension medicine, then the machine learning model is basically just repeating the doctor's diagnosis. It's not actually learning to predict whether a patient will get hypertension or not. Now, two quick things about this example. The first is, it might seem like a bizarre thing to train a model on such data, but it's actually in practice really hard to tell which features are legitimate and which ones are not, simply because of the vast number of features that are available today. So many of the data sets that are used for training these models have thousands of features in the data, and it's hard to go over each one of them one at a time to say which features are legitimate and which ones are not. The other thing about this example is, if we go back to Epic's sepsis prediction tool, one reason for why the tool's predictions were exaggerated or the tool's performance was exaggerated was because the tool was doing something very similar. So there, the tool was being used to predict whether someone would get sepsis. And one of the features was whether a doctor had prescribed antibiotics. Now, in many cases, antibiotics are only prescribed after sepsis has been diagnosed. And so even in these cases, the model was essentially predicting what the doctor had already diagnosed. But these examples were still counted as a success for the tool's predictions. And that's what led to the inflated accuracy estimates. And also, like the example that we just saw of predicting antihypertensive drugs as a feature, this exact error has already occurred in one of the existing papers as well. So in particular in a peer-reviewed paper published in the Journal of Medical Internet Research, the authors claimed that they can predict hypertension as soon as a patient arrives to a hospital. But 5 of the inputs to the model that were extremely important for the model's decisions were whether the person had already been prescribed antihypertensive drugs. Now you can imagine if someone is already using antihypertensive drugs, then predicting whether they have or have they don't, whether they would have hypertension in the future is kind of a moot question, because you can basically just use previous diagnoses to predict someone's future illness. All right, moving on to a third kind of leakage. The third kind of leakage is sampling bias. That is when a machine learning model is trained on one specific type of population, but then it is used on a very different kind of population. So for instance, if you train your model on books in English and then try to predict it or predict its performance on books in other languages, the model is unlikely to do very well. Now, once again, if this example seems hypothetical or nonsensical, here's one sort of recent study which found that many machine learning-based science papers are doing exactly that. So in particular, this paper that was published in Nature Machine Intelligence by Michael Roberts and his team found that of the 62 papers that they assessed on using chest radiographs for distinguishing or predicting whether someone would get COVID, they found that 16 of these 62 papers were actually just distinguishing between adults and children, because all of the examples of people with COVID were from adults, but all of the examples of people without COVID were from children. And so essentially all the model was doing was detecting whether someone is a child or an adult based on their chest X-ray, which turns out to be a surprisingly easier problem compared to detecting whether they actually have COVID or pneumonia. And this is also, again, very similar to the example of wolves versus dog prediction that we saw earlier, where instead of detecting whether an image is of a wolf or a dog, we were actually predicting what the color of the background is. Here's another example of a very similar error. This is an example where a chest X-ray is used for predictions of health issues. And it was found that instead of using information from the lungs or from the actual X-ray itself, what the model was doing was essentially relying on a hospital's token on the top right-hand side and using that as a proxy for whether someone would actually get an illness. So in other words, the model had no sort of conception even of what a health illness is, or what is a healthy versus an unhealthy image of lungs. All it was doing was detecting what the token on the top right-hand side of the image was. And based on this, it was getting high accuracy because in many cases, the technicians used like a different token depending on whether someone was healthy or unhealthy, or even between different hospitals, the rate of healthy versus unhealthy patients differed quite a lot. Okay, so we've seen a few examples of leakage in real-world applications. How prevalent is this like phenomenon in machine learning-based science? So in a recent paper, which was just published in Patterns by Cell Press in 2023, we found that 294 papers across 17 different fields are suffering from leakage. Now, this is a lower bound. This is only the number of papers we were able to find from our literature review. And we found that leakage causes reproducibility failures in each of these fields. The point, or the fact that was most concerning was that every single field is independently rediscovering leakage as one of the issues that causes reproducibility errors. So in particular, we found that in many cases, when fields discovered their issues, or when fields that had just adopted machine learning discovered there were these leakage issues, they basically reported their findings without recognizing that it is a much larger, more widespread phenomenon that affects many different fields and many more papers beyond just their own field. Now, leakage is especially a concern for scientific research that uses machine learning-based science. In fact, one of the sort of main differences I want to highlight here is that many of the applications where machine learning is become prominent are lie in engineering applications. So these are products or services that you use in the day-to-day, things like your email spam filters or Google Photos or social media image tagging. And I want to say that I mean, this is kind of a controversial claim, but I want to sort of justify why these applications are less prone to leakage compared to machine learning based science. So in the typical machine learning application in the industry, or a typical engineering application of machine learning, the initial phases are you build a machine learning model based on a vast data set. Then you validate that model using the train test split that we talked about earlier. And finally, you deploy this model in a real world application. The key thing here, though, is that once a model is deployed in a real world application and users are actually using it in the real world, there are lots of ways to identify errors. A lot of these models are deployed to like large numbers of people. There are ways to report bugs or errors in the model. And once these errors are found out, engineers are usually incentivized to fix them as quickly as possible. So in other words, there are low stakes for a lot of engineering applications for making small errors. There are quick ways to fix these errors in the production setting that is actually used for engineering applications. And most importantly, in many engineering settings, the key reason for developing the models is already determined before the model is actually deployed. So the only question we want to answer is which of a given number of machine learning models is most effective at solving a particular task. We're not really interested in the absolute performance numbers. In contrast, in machine learning based science, the first two steps are very much the same. You do build machine learning models based on data sets from the task at hand. You do validate them as, if possible, using a train test split, though we've seen sometimes that doesn't happen also. But the key difference between these two settings is that instead of deploying these models in the real world, the last step of a machine learning project is often a publication. And that means that there is not really a mechanism for finding these errors. And more importantly, the people making these machine learning models are neither incentivized to find out and report on these errors, nor are they incentivized to fix the historical record. So because of these two reasons, errors take a long time to uncover and challenge. In addition, in a lot of cases, the stakes are really high. So sometimes a few false findings and the presence of leakage in a few papers can lead to widespread consensus about machine learning in a field. And most importantly, in many scientific applications, it's the absolute performance numbers that we care about, not the relative ones. For instance, if we want regulatory approvals for a particular application of machine learning based science, we actually really do care about what the exact accuracy of the model is, as opposed to only caring about what the relative accuracies are. So for all of these reasons, it seems like machine learning based science is in a worse position when it comes to leakage compared to engineering applications. And in fact, like a personal anecdote from my own experience is that before I started my PhD, I used to work at Facebook as a machine learning engineer. And a lot of the times when we deployed these products in the real world, we would actually encounter errors or edge cases that we hadn't thought about once the models were deployed, especially for lower stakes settings. And what it actually meant was that we were able to fix these errors extremely quickly, whether it was through smaller rollouts initially to get people's feedback, or even through a bit larger rollouts when we could sort of fix these errors in production. So in other words, Facebook's tagline of moving fast and breaking things did not help them a lot in other societal matters, but actually it was quite enough for machine learning applications that they actually deployed in the real world. The last point that I want to emphasize is that detecting leakage is not enough to fix it. So in many cases, we can actually identify that leakage has occurred, but we don't always know what the best way of fixing leakage is. In other words, fixing leakage is an open research problem. So I think an interesting example here can be the apocryphal story of the US Army AI tank classifier, which was used for distinguishing between the US and Soviet tanks. And it was found that it actually had exceptional accuracy. On closer investigation, it was found that much like the wolf versus dog example, it suffered from leakage because all of the examples of Soviet tanks or all of these pictures of Soviet tanks were taken on a bright and sunny day, but all of the examples of US tanks were taken on a cloudy day. And so it turned out that the classifier was great at classifying weather, but not really great at classifying what country a tank is from. Now, the thing to remember here is that the weather distinction sounds easy, but we cannot possibly account for all of these spurious correlations between the background and the outcome of interests. So even if we fix like the weather, we take all images on a sunny or a cloudy day, there might still be other hints in the background. Things like what the foliage of trees look like, or whether there are electrical wires in the background, or all sorts of other things which can give away the geographical location of the photograph. So this means that even if we are aware of leakage in a machine learning model, we cannot easily fix it. Now let's look at the impact of leakage in a particular case study from one of our previous works. So in particular, from a 2016 paper, I want to highlight one specific line from the abstract. The abstract of this paper claimed that we can predict civil wars with exceptional accuracy using machine learning. So the last line of the abstract here is that the performance of random forests is excellent. Random forests is a type of machine learning model. And they claim that the AUC, that is a measure of accuracy, is above 0.9, which is exceptional. Based on this result and based on a few other results that followed it, there was widespread consensus in the political science field that we can predict civil wars with a high accuracy. So in particular, this is a Science Perspective piece from 2017, which said that we can have a much higher overall predictive accuracy by the techniques outlined in the previous paper from Muchlinsky et al. Now, back in 2021, my colleague, Professor Arvind Narayanan, and I looked into this, and we wanted to understand what makes random forests, that is machine learning models, so much better at predicting civil wars than all of the techniques political scientists have been using for like over 2 decades at this point. In particular, the main sort of such technique is logistic regression that has been used in the field. What we found out instead was that the entire difference between random forests and logistic regression models came down to leakage. So there was leakage in the model. And once we fixed that leakage, we actually found out that random forests perform no better than decades-old logistic regression models. So on the image on the slide, the top point here, that is the model which has an AUC of 0.9, is the random forests model proposed by Muchlinsky et al. And the other 3 on the left-hand side are all examples of logistic regression that had been proposed for 2 decades previous to the random forests model. And it turned out that when we fixed leakage, the random forests model on the right-hand side performs no better than one of the logistic regression models, which calls into question the entire sort of premise on which the scientific consensus around machine learning models being good at civil war prediction was based on. In fact, we could go one step further, and we saw that there were 4 major papers which had claimed that machine learning models outperform logistic regression, which was this older method. We found that all 4 of these papers failed to reproduce, and leakage was a cause of reproducibility failures in each case. And in each case, when we fixed these errors, machine learning methods performed no better than 2 decades-old logistic regression models. So once again, this is an example of why leakage is especially important to address in machine learning-based science. It's because scientific consensus, it can establish false scientific consensus about the use of machine learning for solving a scientific problem of interest. And it can take years to challenge this scientific consensus, even once these issues are found. So how can we address these issues, especially in machine learning-based science? I think for a lot of the questions that we've asked here today, I think, especially for machine learning-based science, we can actually learn a lot from existing standards which have been proposed by existing scientific fields which have already seen these errors. So in particular, in the health research space, there's a tradition of using checklists to improve the quality of health research. So the Equator Network has published around 500 different checklists for improving the quality of healthcare research. And based on this sort of vast repository, it's been shown that in a lot of cases, checklists actually do a pretty good job of improving the quality of health research. So we took a leaf out of this playbook and we've developed something that's called the reforms checklist. So in particular, 19 researchers across computer sciences, social sciences, data science, biology, all of us came together to come up with a checklist for machine learning-based science. And we proposed something called the reforms checklist, that is reporting standards for machine learning-based science. So the reforms checklist consists of 32 questions for different stages of the machine learning pipeline. And it goes over the common pitfalls and best practices in each of these sections, including like the study goals, whether the study is reproducible, whether there's leakage, and so on. So this is one attempt. I'm not like it remains to be seen whether this attempt would be successful in helping improve the quality of machine learning based science somewhat. But I think from past research in the healthcare space, I think there's some reason for optimism. In addition to the checklist, we've also released a detailed set of guidelines for how to fulfill these checklist items, as well as a survey of past literature, which can aid researchers when they're performing machine learning-based science. And the checklist and the effort, all of it is available on the website on the slide, reforms.cs.princeton.edu. All right, so far, to do a brief recap of what we've seen that in many cases, companies make tall claims without transparency, and that AI research is suffering from a reproducibility crisis. Many of the machine learning-based science results that we've seen are exaggerated or over-optimistic, and this issue is systematic. That is, in many cases, we don't really know what the best next steps are, apart from adopting more transparency. So what both of these things mean today is that many of the prominent AI results that we've seen are exaggerated. Now, this is like the current state of affairs, and we've talked about like researchers as well as companies and their role in making AI hype persist. We'll now look at what journalists can do both to sort of further the AI hype, but also to curb it. So this brings us to the fourth part of the talk, that is what the role of journalists can be and should be in the AI research space. So on the slide here is a list of all of the headlines that came about when Microsoft launched its new Bing AI chatbot. The New York Times said that Bing's AI chat, I want to be alive. The Washington Post reported, the new Bing told a reporter it can feel or think things. And the list goes on and on. In many of these cases, it's implied that AI is sentient or that AI has like the ability to feel or think things or be alive and so on. Now, a lot of these headlines are actually misleading. Current AI systems are closer to like computational systems than to anything resembling humanity. And in fact, if we go back to the history of chatbots and if we go back to the history of how chatbots have been perceived by people, we can see that similar issues have been around for like over 6 decades now. So here's an example from Joseph Weizenbaum in 1966. He created a chatbot called Eliza. Eliza was a very basic chatbot. All it was doing was essentially rephrasing users' inputs as questions and posing them back to the user. So for instance, here's an example chat. Eliza would start off with something like, is something troubling you? The user would reply, men are all alike. Eliza would just reply with another question. What is the connection, do you suppose? And so on. The key thing is all of these questions were hard-coded. So this was basically like closer to an Excel spreadsheet than any form of AI. And yet many of the people who actually used this system came away thinking that Eliza was actually a person. Many people refused to accept that they were actually just talking to a computer program. And people thought that they could use Eliza for therapy or for all sorts of things, which is very similar to the situation that we find ourselves in today. Lots of people have made claims about AI systems being sentient or being resembling humanity and so on. And even though the systems that we have today are far more sophisticated and advanced than the rule-based system that Joseph Weizenbaum constructed in 1966, I think some of the issues remain the same, especially in terms of anthropomorphizing AI systems and thinking of them as human-like. Now, this is not the only issue with journalism. I think there are like a whole slew of issues. One other thing that's particularly common in articles on AI is that there are concrete performance numbers accompanying new tools or new AI systems. But in a lot of cases, there's never enough space to identify or to inform the reader about what these performance numbers even mean. So going back to the Civil War prediction example for a minute, let's say we had a news article report that a Civil War prediction algorithm has 99% accuracy. Now, this might indeed seem like an exceptionally high accuracy number simply because it's so close to 100. But it seems much less impressive when you consider that a model can get 99% accuracy by simply predicting that there will always be peace, simply because the number of data points for which there is war is much lower than the number of data points for which there is peace. But there is often not enough space in a news article to inform readers about all of these important questions to contextualize these performance numbers. That is, what data was the algorithm tested on, what happens to the model's accuracy over time, and so on. And here's an example from, I think it was from Bloomberg, which reported that the algorithm has 90% accuracy for predicting crime. In fact, the paper as well as the article were heavily criticized for taking these performance numbers out of context and for essentially making exaggerated claims about the algorithm's performance on a real world task. Yet another example of AI reporting intentionally or unintentionally misleading the public is through, again, anthropomorphization, but this time in images. So a lot of articles that talk about AI use images of robots when depicting AI systems. For instance, here you have a humanoid robot arm shaking hands with a human hand. If you look closely at this article, the article is actually talking about a pattern recognition system that is just something that's used for crunching numbers. But the cover image alone makes it seem like what we're actually talking about is a humanoid robot. Whereas in reality, this system is closer to an Excel spreadsheet than any form of humanoid robots. Similarly, here's an example of how hard it is to remove this reliance on robot images. So here's an article published in the LA Times about our work, so my and my advisor Arvind Narayan's work on challenging AI hype. The article itself uses an image of a robot, and the writer actually acknowledges that the illustration accompanying the article sadly has an image of a humanoid robot. I think this also highlights one of the key tensions that accompanies a lot of writing about AI, which is the click-driven nature of journalism and the lack of funding, or the systematic lack of funding that journalism is seeing today. So in particular, a lot of news outlets have become heavily reliant on clicks in order to fund themselves. And this also means that catchy images of robots are more likely to accompany AI articles on AI. Now, I give this example to point out that it's not just about individual journalists not doing a good job. I think that's not really the key issue. And if we focus on individual journalists going wrong, I think we are missing the bigger structural piece that is actually leading to a lot of the hype around AI, which is that we need more systematic investment into public benefit journalism. And we need to move away, or we need to find ways at least to challenge the click-driven nature of technology journalism, but also journalism in general, to get into informing readers more thoroughly about artificial intelligence. Now, we did something more systematic to look at how AI research or how reporting on AI research can go wrong. And we found 18 different pitfalls in the different kinds of AI research or journalism about AI research. This includes things like over-reliance on PR terms, or not talking about the limitations, or attributing agency or sentience to AI, or even suggestive imagery, like we saw in the last two slides. So coming back to our recap for a minute, so we've seen that companies and researchers contribute to AI hype, but it's actually uncritical reporting on AI which puts these AI results in front of the public and leads to a perpetuation of this feedback loop of misinformation among readers about what AI can and cannot do. But at the same time, journalism has also played an amazing role in bringing to light the limitations of what AI can and cannot do. Many of the examples that we've seen throughout this presentation, like the Epic sepsis prediction tool, or the Dutch welfare fraud scandal, or even Oregon's child maltreatment prediction tool, all three cases, it was AI journalists or journalists who were looking at AI systems who brought these issues to light. And this kind of work was so important to bring to light what is actually going on with AI. Now, here are a few other examples of how how journalism can actually help the reporting on AI. So one very basic question to ask of any AI system is what's in the training data? And more particularly, how well does it match what the model will actually be used for? Because at the end of the day, all we are using AI systems for is real world tasks, which might not always resemble what's in the training data. So here, a very good example from a recent report was Washington Post's work on looking at the data set, the C4 data set that's used for training a lot of AI systems, and essentially making a very readable and digestible version of what constitutes that data set. What sources are included, what sources are excluded, which of these sources have especially problematic materials, and so on. Another example of journalism which shines a critical light on AI systems is journalism that actually does reevaluate real-world applications of AI. So on the left-hand side was the groundbreaking investigation from ProPublica, which brought to light many concerns about fairness in AI systems. It was an investigation of the Compass tool that's used for recidivism prediction. On the right-hand side is a more recent example just from last week about predictive policing software being terrible at actually predicting crimes. So I think this ties together what we saw about predictive AI not really working in the real world, as well as how investigative journalism or journalism in general can shine light on the limitations of AI systems. And finally, an interesting question, or like an important question to ask every single time an AI system is deployed in the real world is, what are the downstream harms? And I think this question can lead to many insights for every single AI tool that's currently deployed. So again, on the left-hand side is Epic's sepsis prediction algorithm. Stat News, and in particular, Casey Ross, played a major role in bringing to light the harms of the algorithm and how developers were failing to evaluate it properly. On the right-hand side is an example from the New York Times, which actually showed that many startups in AI are selling face recognition software or ethnicity recognition software, specifically targeted towards the minority Uyghur population. So I think all of these examples show that there are many positive instances of journalism actually leading the way in pointing out how AI systems fail us and making clear where AI systems can and should be used, but also making clear what the limitations of these systems are. So I think that's all I have for you all today. I should note that a lot of this work is joint work with my advisor, Professor Arvind Narayanan. And we also have a blog and newsletter called aisnakeoil.com if any of this was interesting. And it was also based on a collaboration with Ari Sen and Hilke Shellman. And in particular, we have a piece at Columbia Journalism Review earlier this year titled How to Report Better on Artificial Intelligence. So with that, I'll open it up for questions. I think we have around 20 minutes. So hopefully we have a lot of time to discuss. Thank you.
Thank you very much, Sayash. Fantastic talk. People with questions, I invite you to come up to the microphone here. As you do that, I'm going to throw out one question. So it seems to me a lot of the problems of leakage and predictive AI, they almost pale in comparison to the generative AI issues, and especially flagging ChatGPT-4 and its capacity to lie, for example, it can't solve CAPTCHAs. So it says, I have a visual impairment. And that leads the people behind ChatGPT-4 to look for ways to avoid what's called shutdown behavior. So the worry that these AI programs could develop the ability to avoid being shut down if they were going in a direction that would be harmful to the broader society. Do you think there is a disparity there between some of the concerns about predictive AI that are very specifically limited to particular fields of science, particular ML programs, versus the broader societal impact of what these other programs might actually be capable of?
Yeah, that's a great question. Thank you, Rich. So I think it's definitely true that just by virtue of being deployed so broadly and affecting so many people, I think generative AI risks deserve a lot of thought and contemplation. I think by some estimates, ChatGPT 4 has, or ChatGPT actually has reached around 200 million users. So that just magnifies the potential for harm when an AI system becomes a consumer technology application. At the same time, I do want to push back against some of the purported risks of tools like ChatGPT. So the particular risk that you describe of shutdown systems, I think is, like, to be quite honest, a bit overplayed, simply because of the fact that the tools that we have today are in no shape or form close to even being at that level of agency. So for instance, I think a lot of times it's easy to fall into like the trap of anthropomorphizing these tools. But I think at the end of the day, it's important to remember that tools like ChatGPT, all they're doing right now is predicting the next word. They're trained to just predict the next word in a like series of words that's been said so far. And as long as humans are not using these tools or giving control to these tools for real world tasks, like using LLMs to, let's say, power our nuclear operations, or using LLMs for consequential real world tasks, I think there is no sort of risk of such shutdown behaviors. So I think the key thing to look for is, where is it that we as a society are handing over some of the control to language models, or where is it that we are hooking them up to real world systems which might actually have a lot of consequential impacts, rather than the tools themselves being agentic in some way, or the tools themselves leading to shutdown. So I think it's much more important to question who is hooking up language models to consequential real world tools, and who is sort of using these tools when they're not fit for purpose, much more so than the tools themselves acquiring the ability to avoid shutdown behavior. And so in that sense, I think at the end of the day, the answer is always like a human or an organization or an institution which is making that decision. And so I think it's always important to sort of focus on that part of the deployment chain, rather than the tools themselves leading to like shutdown, avoiding shutdown behavior, or their tendency to lie, or even sort of make up factual stuff, or like not factual stuff.
Thanks, Sayash. We have several people lined up to ask questions in the room. You can't see them, but let's start with the first question.
Hello, my name is Kirsten. I'm from Carnegie Mellon University. You gave a lot of great tips for journalists on how to cover AI. However, when working for a university, you have to balance accurate coverage with promoting the university. Do you have any suggestions for us in a way that we can cover AI accurately while still celebrating the work of our professors and our students?
Thank you, Kristen. That's a great question. And actually, it points back to one study, or I think it was an article from Nature, which found out that the root cause of a lot of hype around research, and the hype around research in scientific coverage, is press releases from universities. And so you're absolutely right that I think it's important to be accurate when we're talking about this. I do think a lot of the sort of problems or the issues with journalism that we highlight, or the issues with reporting on AI that we highlight, can be fixed while still being optimistic, or still covering the research advances well. So for example, instead of using images of robots, one recent article actually used an image of like an all-seeing eye when they were talking about an AI system, which is just as catchy, but it actually highlights the negative impacts of AI research as well, which is that a lot of AI research can turn into surveillance. So I think finding these alternative mechanisms can become really useful at the end of the day to counter some of the hype, maintain accuracy, but also make sure that the research that you're talking about gets amplified.
Thank you.
Hi, my name is Liz Landau. Thank you so much for the great talk. I guess I wondered, as we're thinking about all of these pitfalls of AI at the moment, how will we know when we do approach a sort of the next big milestone in the sort of path towards like not even sentience, but like closer to it, I guess? And also like, how far away do you think that we are from like a really big like next step in that direction? Thanks.
Thank you. Yeah, that's another great question. I think it's always hard to make predictions about the future. A lot of my work is on countering any such predictions about the future. So I won't make like a specific guess. But I do think there are reasons to believe that, we are approaching more general systems or systems that can be used in a variety of scopes and purposes. That said, at least for right now, I prefer to think of these as tools which are general purpose rather than anything like resembling sentience or consciousness. And so if we look at them as tools, we actually have a lot of historical analogies to reason about what their impacts on the real world would be without necessarily speculating about what their future capabilities could be. So here's one example. If we look at GPT-4 or the latest wave of AI tools as tools that can augment human behavior, but also replace people in some sense, then the natural analogy is to general purpose technologies. That is, technologies which can be used in a variety of ways and which have a transformative effect on society. So there we can draw on like the Industrial Revolution if we go back hundreds of years, but we can also draw on like the internet if we go back 20 years and examine what impact the internet had on our way of communication, on our way of doing commerce, on our way of like relating to each other as human beings. And I think that would offer a far more useful analogy in terms of thinking about the impacts of AI. So for instance, if we look back to the previous waves of automation, we've seen that automation leads to a lot of short-term shocks in terms of employment and labor displacement. But we've also seen that it's not always easy to predict which jobs would be impacted most, simply because automation, on the one hand, replaces human labor because it's cheaper. But on the other hand, it also makes it much cheaper to offer goods and services, which means that there might be more of those goods and services produced. So one example that I like here is that the prevalence of the automated teller machine, the ATM, actually led to an increase in the number of bank branches simply because it was so much cheaper to create a new bank branch as opposed to staffing it with all the cashiers and whatnot. So this is, I think, known as Jevons paradox in economics, and it makes it hard to predict the future impact. But I think more broadly, drawing from the analogies of past waves of automation, but also previous general purpose technologies, might be much more useful as a way of reasoning about the social impact of tools like GPT-4.
Hi, Sayash. Great talk. I'm Siddhant. You raised two problems. One is the bad science, and one is the deployment of these tools that sometimes clearly have like surveillance motives. Are these problems connected in some way? Are governments and corporations just falling for bad science, or are they actively seeking these tools out? What do you think?
That's a great question. Thank you, Siddhant. So I think, at least in our framework, I do think a lot of the surveillance technology has the capacity to harm people precisely because it does work. It can like work well already to some extent, but more crucially, I don't think there is any upper bound on how well surveillance technology can work. Simply because for AI for surveillance, the ground truth is already set in stone. Like given an image of my face, you cannot really say that there's any noise in the process by which a future image of my face would be generated. But given an image of my other characteristics, things like what my GPA was, or I don't know how well I did at my previous job, there is a lot of variance in how I might behave at a future job. There might have been circumstances that were private to me that no model could ever access. There might have been shocks, things like an emergency room visit, which blows up and makes a terrible financial consequence on me, or like winning a lottery, which might have an amazing financial consequence. And all of these things can't be predicted in advance by AI models. So I do think there is like a fundamental difference between predictive AI, which is essentially dubious, and between generative and perception AI, which does work very well to some extent. And so the reason for ethical concerns between the two things are extremely different. Like for generative and perception AI, the ethical concern arises only when these tools actually start to work very well. But for predictive AI, the concerns arise because the tools don't work at all in many cases. Now, that said, there is definitely hype in generative and perception AI as well. So for instance, there are lots of claims made about like the ability of AI models to replace lawyers, or the ability of, I don't know, all sorts of knowledge work being replaced by AI, which in many cases is more hype. Jeffrey Hinton, one of the godfathers of AI, back in 2016 actually said that a radiologist is like a coyote who's over the hill but does not yet know it. And in 5 years, we'll stop needing radiologists. So we should stop training radiologists now. 5 years later, or actually 7 years later at this point, we have a massive shortage in the number of radiologists that are being trained. So I think there is still like the some amount of hype in the claims of how much generative and perception AI can work. But broadly speaking, I think, at least in terms of being useful to some extent, both of these types of AI systems have like a base on which they're presumed to be useful. Whereas for predictive AI, it's really just like a very different league. There's very little evidence that these tools work in many scenarios.
Hi, thank you for a great talk and thank you for your work as well. So my name is Harini. I'm from Dartmouth College. I have actually sort of two questions that may be related. The first is actually a step back in looking at the algorithms themselves. Like, I think at the heart of the problem is the fact that these are black boxes, and so we don't really understand the parameters. Is there work that is advancing that knowledge? Are there attempts, and what is the progress on understanding these algorithms and what they are actually doing? And the second part is actually to do with some of the examples you showed where the backgrounds were kind of, confusing the results. So is there a way to kind of allow the algorithms to learn while also directing them, like saying, look at these pictures, but ignore the background, so to say?
Yeah, that's a great question. So I think on the first part, definitely there's like a lot of progress being made in a field called mechanistic interpretability, I think, but more broadly in interpretability of AI systems in general. That said, I think in a lot of cases, what we need is not an understanding of like what the internals of the system are doing, but how a system is operating at like a little bit of a higher level. So let me give you an example. So for a lot of cases, the limitations of current AI tools lie in their inability to generate factual information, for instance. Now, in order to get at this inability to generate factual information, or in order to get at this tendency to like fabricate information, I think we don't really need to know what's happening in each layer of a neural network or what's going on inside the black box. It's quite enough to use this model as a black box and to see how well it works in like the different kinds of scenarios where we're planning to use it, what its limitations are. And on the whole, I think it's already enough to have access to these systems in order to understand these limitations. So there's like a fascinating piece called The Fallacy of Inscrutability in AI, which says that, yes, in some cases, we do need interpretability in order to understand what a system is doing. But for a large number of socially relevant outcomes, we actually don't need interpretability at all. And this is what the author calls the fallacy of inscrutability, that AI systems being inscrutable at a mechanical level does not really mean that we can't understand how these systems work in the real world. For the second example, for the second part of the question, where you asked, is there work on directing AI systems to what the relevant object of interest in an image is? Yes, definitely. I think one promising technique is called contrastive learning. There's been a lot of interest in contrastive learning recently. There are like basically an entire stream of research in that area. That said, I think I think we made some progress in that area. I think broadly, the problem of spurious correlations is still unsolved. So we do have like promising research directions, but I think it would be a stretch to say that we are anywhere close to like the final solution or the final word on spurious correlations in machine learning. We also have a few questions on the Zoom chat. So maybe I could quickly go over like one or two questions right now.
Actually, if Sayash, if you could, we have two more questions in the room here, and then we're going to adjourn. If you could respond separately to the online questions, that would be fantastic.
Okay, perfect. That sounds great.
Okay, thank you.
Hi, I'm Ankita. Thank you for the great talk. I kind of wanted to follow up on the tips that you gave, like journalists to follow once you're writing pieces on AI. Especially the first one where you said, like, go and have a look at what's in the training set or in the training data. So like for journalists who don't have, let's say, computer science background, like, what does it mean? Like, can you distill it out for us? Like, what should we be looking when we are reading the reports in the training data that might give us an idea that maybe this is too early to fall, or this hasn't taken X number of variables into account? Like, what are the signs we should look for?
That's a great question. I think one of the key things is to to just go back to the analogy of pattern finding machines. So just to think of machine learning as something that finds patterns in existing data. Now, what this means is that anytime the training data differs from the real world applications of a tool, there is a mismatch between the developer's claims and what is going to happen in the real world. So one example is the wolf versus dog example. If a machine learning developer is claiming to use that system for predicting which species or detecting which species is there in an image, and all of the images of wolves are on a snowy background and images of dogs on a grassy field, that does not really generalize to the real world where there might be images of wolves in a grassy field. So at a very high level, I think just looking at the similarities between the training data and the real world application and where it will be deployed is one of the most important things. I think more specifically, a lot of examples in the last few years have focused on bias in these models. So say a machine learning model is trained only on images of a certain race or of people in a certain demographic group or a certain age or a socioeconomic background. I think a lot of this reflects in the outputs of the models as well. And so in many cases, it is very useful to find out what the proportion of these things is. And you don't necessarily need to be like a tech expert to do this, right? Like you can pick out like 100 random samples or 500 random samples and just very quickly annotate them yourselves or just look at the data yourselves in order to see what these distributions are like. And I think that is already enough to give you a sense of what kinds of patterns would an AI system predict and what places it would work poorly on. So for instance, an example of a concrete data set here is the Lion 5B dataset. So it's a collection of 5 billion images that's used to train lots of text to image models, things like DALL-E or Stable Diffusion by Stability AI. Now, this dataset is publicly available. So there's nothing stopping any of us from just going on to its URL right now, looking at like 50 images or 100 images and trying to classify them. And actually, there are also some tools meant to explore these datasets. So you can actually like filter the dataset just to include images of humans or just to include images of like, I don't know, e-commerce products or whatever. You can try to look at a specific subset to see what's in the data. So I think that can be by itself be like a really powerful tool to get to know what's wrong in the training data.
Thank you.
Hi, I'm going to actually talk to the camera so you can see my face. My name is Karen McNulty Walsh. I am at Brookhaven National Laboratory, and I think in my general surroundings and with all the examples you gave, there's a lot of suspicion and concern about these applications, and fully understandable. But I'm coming from a world where I have a lot of scientists who are using AI and machine learning to sort through data sets to improve the performance of computers, for example, in drug discovery, or sorting through data sets of particle collisions to find interesting events and to predict the properties of new materials for materials discovery for better batteries or solar cells or things like that. And so when I get into these conversations with people who have all these concerns about machine learning and AI, I kind of want to have messages to say, yeah, but it's not all bad. There are some of these useful purposes that might actually improve our lives in very direct ways or improve the pace of scientific discovery. So I'm wondering if you can comment on that, if that's true, and how you would advise us to kind of communicate the difference between sort of some of the pitfalls and the promise.
That's an excellent point. And I should also clarify that fundamentally, I think I'm an optimist about many of these AI tools. And so the only reason like Arvind and I started the AI Snake Oil blog was because I think in a lot of ways, the hype is even reducing our ability to reason about these advances very well. So all of the examples you pointed out, I think are perfect examples of what AI can do well. Drug discovery, discovering new materials, and so on. I think one way to think about what makes a problem really amenable to AI versus not is whether once the process is done, whether it is easy to verify that the solutions of a problem are correct. So for all of the examples that you pointed out, whether it is material science or drug discovery, I think the key differentiator is that the last step of the process is not just an AI system saying that this material or this other material would be good in the real world or it would have suitable properties. The last step is actually someone actually manufactures that material and then they can verify that in the real world. And that's the standard for evidence. So seen this way, again, I think AI is a tool in like a bigger step. And the last step is actually human verification. And I'm very optimistic about the use of AI in tasks which need human verification at the end. So in general, like if you have like a large search space and you narrow it down to like 5 materials, which are then tried by a human expert, or if you have like a large space of what could constitute a protein, and then you narrow it down to like a reasonable number of sets of proteins that you can then manufacture, say in a wet lab, or test them out in the real world. I think those are precisely the kinds of problems where AI really does shine right now. I think the key difference between that and like a lot of places where there's snake oil is that there is no easy way to verify the solution. So companies like Retorio or all of these companies sort of claiming to predict fraud or job performance, they basically can get away without any evidence because there's no one coming back after 2 years asking these companies about, hey, like this prediction was actually wrong. They're not really being held accountable to their final prediction. And in many ways, the AI system is actually the end result of the pipeline rather than something that is later verified by humans. So I think for me personally, this distinction has been really important, whether AI is used for narrowing down from a large space of problems to a small space, which can then be verified, versus AI being like the final word without any human input.
I just want to say, Sayash, I wanted to commend you, knowing what you know, to have the confidence to give such a comprehensive talk without having a shelf full of books behind you. I mean, that is gutsy. If Sayash is still here, I'd like to say thank you. Thank you again for a fantastic talk.
Thank you so much. Thanks for having me.